Hey all, Software Brother 1 here. I just wanted to put a video together on how to solve the maze problem in The Farmer Was Replaced. The reason I wanted to do a video for this was because when I came across the maze in this game, I thought that for someone who's a beginner in programming, this probably seems super daunting because A, it's completely different to any other crop that you are harvesting. If you're doing carrots or wood, at the very least you can create a nested for loop that goes across the entire grid, harvesting that crop. But with the maze, there's a whole different structure to it of, initializing this maze with different actions. And then the actual way to solve this uses an idea of recursion and depth first search that are concepts that don't necessarily come easily to a new programmer, but the way that you solve a problem like this can really help you to understand computer science. And even though the idea of like depth first search and recursion and the other concepts that are needed to solve this maze sound kind of daunting, they're actually pretty straightforward and elegant once you understand them. And I wanted to go through that so that you guys who may be blocked by this part of the game, you can progress past it and also understand maybe a few new computer science concepts. So let's pull up the documentation for mazes here. And if we look at this, a few things stand out. So what we need to do is we need to use weird substance on a bush, and then we can use a specific amount of weird substance on the bush to create a maze. This is kind of useful because if we use a smaller amount of weird substance on the bush, we'll actually get a smaller maze that we can run on. And this is useful for testing out things before you've got your algorithm all sorted out. It's always better to test on a smaller environment if you can when you're first developing your algorithm, because it's a lot easier to catch issues on a small scale as opposed to doing the entire 10 by 10 grid. So we're going to do that when we're developing this. We're going to try it on a smaller maze first. Another important thing way down here is that mazes do not contain loops unless you reuse the maze. So you have the ability at the end, instead of harvesting the treasure, to essentially continue the adventure and try to find a new treasure. And this can compound the amount of treasure you find. But this algorithm that we're developing, it won't work like that. This algorithm is going to depend on the assumption that this maze doesn't contain any loops. And we're going to do that because it's just easier to implement this kind of algorithm. You'll see later why that is. So it's pretty difficult when you first read the documentation to know for sure how everything works. I mean, there's a lot of information here, a lot of steps to actually set up the maze, and then what do you actually do after? And it would be very difficult to go straight into trying to write an algorithm, even if you do understand the documentation. So what I like to do is I like to at least visualize what's going on with this new challenge before I dive into the code. And the best way to do this, I've found, is setting up a set of helper functions. And right here, I've got a lot of windows open, and all of these act as helper functions that will help me walk through the entire process of solving a maze. So let's just run through it. Everything is already cleared already, so I don't really need to run a clear, but I will. The next step based on the documentation is to plant a bush. So let me go ahead and plant a bush. This is because the way to start a maze is to use a weird substance on a bush. So now that this bush exists, we can use this little formula here. The reason I set up this formula is because the way to set up a specific dimensions of a maze is to use that dimension, the desired dimension number, which is going to be 5, and multiplying it by the number of unlocks you have on the unlock tree, and then using that amount of weird substance on the bush. So let me just go ahead and run that. Oh, and I had a print in there. Let me remove that. We don't need that print. And there you go. Now I have a 5 by 5 maze that I can try to solve. And now what I can do is, using these little helper functions for movement, let me move around this drone. So I can see that as I move through this maze, I can go in certain directions, but wherever there's a wall blocking me, I can't actually move in that direction, which makes sense. And nothing happens. Something to keep in mind is that as I attempt to move, that actually does cost some time as far as leaderboard runs go, but we don't want to worry too much about that. The goal of this is to actually solve the puzzle in the first place. So if I move east one more time and I move north, now I'm on top of the treasure. And what I can do now is I can harvest it. And there you go. I solved the maze. And that helped me visualize exactly what's going on. Now that I have an idea for what operations take place to actually set up this maze, which means clearing the field, planting a bush, using weird substance, now I have an idea of what actually goes into solving a maze, the movement and everything. So now the question is, right now I'm looking at this maze and I'm actually controlling these moves. I can see exactly where I need to go because I can see the treasure. But the robot here, or the drone, it doesn't have visuals into where this treasure is. You programmatically don't actually know where this treasure is. You can just see where walls are by bouncing into them. You try to move south, it won't let you. That's how you know that you can't move south. So what we need to do here is we need to actually visualize, like, what would we do in real life if we were trying to solve this maze? If I was the drone here and I'm trying to figure out where a treasure is, like, what strategy could I actually use? So let's look at this maze right here and let's try to see how we would solve this in real life. So say we're right here at the starting point. We can see that there's two different directions we can go. We can either go up or we can go right. So we can randomly decide that let's try going up first. So we'll go up. We're going up and we've met a dead end right here. We didn't find the treasure, so let's just backtrack to where we were before. So we're going back, we're back here, and we can eliminate this direction. We went this direction, there were no alternate paths in that direction, so we know that it's never worth going that direction again. So now instead, let's go in the only other path that was available to us, which is right. We're going along, and bam, we've hit another intersection here. So let's randomly decide to go right this time first. We go right and we've hit a dead end. There were no other intersections along this path, so let's backtrace and we will eliminate this direction. We know that the treasure is not that way either. So now let's go to the only remaining direction from that intersection right there. We're going along. Oh, we've hit another intersection. Let's randomly choose to go down on this intersection. We're going down, we've hit another intersection. Let's randomly choose to go up on this intersection. We're going up, oh, we've hit a dead end and we didn't find the treasure. Let's backtrace. And now we know that this path does not have the treasure. All right, so now from this intersection, the only available direction was down. Let's go down. And there it is, we found the treasure. So this is an algorithm that we can use to traverse the entire maze and eventually find the treasure. If the treasure wasn't here, we would have gone this way, we would have backtraced. This intersection was already entirely explored, and we would go back to this intersection right here, and we know that we can go to this spot, and this was the only remaining cell that wasn't explored yet. So we know for sure that the treasure would have been there if we hadn't found it anywhere else along the maze. So this is the idea for how visually we're going to explore this maze. We're going to start at a certain point. We're going to look around, see all the available paths that we can go, and then we're going to explore that entire path and all the branching paths from there until we complete it. And if we don't find the treasure within that path, we backtrace all the way back to the beginning of that path, and then we try the next available path from that starting point. So that algorithm that we used to traverse the maze and find the treasure actually has a name in computer science. This is called depth first search. And the idea behind it is that in any data structure that acts as a tree, where a single parent node has child nodes, and those child nodes have their own child nodes, as long as none of those branches are connected, we can actually traverse the entire thing using this algorithm. If we look at this tree, the way we can visualize what we did here was we went from this parent node to a child node, and the child node in this case refers to another intersection that's along one path from that starting position. And we've hit this other intersection here, so what we do is we first try the leftmost node, we travel along here until we hit another intersection, and once we get to this intersection, we try the leftmost path. We travel along this until we get to an intersection. We don't hit an intersection here, we hit the end. So what we do is we backtrack along. Let me use a different color here. We backtrack along, and then we try the next most left node, which is this one. We hit another dead end, we go back. We've tried all the paths on this node here. We go back up and we traverse down to this path and so on and so forth. Once we've finished all the paths on B, we go up to A. There's another untraveled path from A. We go along here, and then so on and so forth until we've traveled through the entire tree here. And in this sense, as long as we've traveled this entire tree, we will find the treasure somewhere along this maze. So it might be hard to visualize, but this is the idea behind the data structure. Now, something important to note is that with our algorithm, it only works if the maze doesn't have any loops in it. And that actually was guaranteed in the documentation. And we can visualize what would happen here if the maze actually did have loops. So if you're starting from position 1 here, let's try this bottommost path here. We go here, and the next step is to try the bottommost path here. From 6, we're trying the bottommost path. From 3, bottommost path. 2, bottommost path. From 1, the bottommost path here is actually down here, so we didn't meet a child node. Our algorithm depended on the fact that we would hit a dead end at some point. But if we don't hit that dead end, we're just going to keep looping over and over again, and our algorithm will never quit. So that's why it's important that we have that assumption that there are no loops in this maze. Now, the one last concept that is important to understand before we do this maze implementation is an idea called recursion. So in computer science, recursion is the idea of basically calling a function within itself. And this is very useful in a lot of scenarios, but it's not super obvious, I feel like, for beginners. So I'll kind of walk through one example of recursion, and I think a really good example of it is calculating a factorial. So the mathematical idea behind a factorial is, say you want to get 5 factorial. 5 factorial represents 5 times 4 times 3 times 2 times 1. So it's a mathematical operation to essentially take the number and multiply it by every number below it. And one important note about factorials is that the factorial of 5 is the same thing as saying 5 times 4 factorial. 4 factorial is the same thing as saying 4 times 3 factorial, and so on and so forth. 3 factorial is the same as saying 3 times 2 factorial, and 2 factorial is the same as 2 times 1 factorial. And this idea of solving a problem by first solving the problem for one stage below is actually more common in computer science than you would expect. So the way this looks mathematically is we're trying to calculate factorial of 5. So we call this factorial method and pass in 5. So if n does not equal 1, which is the case because we're passing in 5, what we're going to do is we're going to return 5 times factorial of 5 minus 1, or 4 factorial. And as I mentioned earlier, 5 times 4 factorial is the same thing as 5 factorial. So what we're doing here is we're calling the same exact method within itself, except we're calling it with a different parameter this time. We're calling it with 4. So we come back into here, 4 is being passed in this time. Again, n does not equal 0, it equals 4. And we go to this recursive case. Now we're returning 4 times the result of this method with 3 passed in. We're going to keep going through until we get to n equals 0. So when n equals 0 comes in here, we hit this base case and we just return 1 straight away. And the base case is very important for a recursive function because otherwise, if we didn't have this part of the code, let me just remove it and visualize that. If this wasn't there, this function would just keep calling itself over and over again, and it would be stuck in an infinite loop, and the program would crash. So the base case avoids that. The base case says if we hit a certain condition, let's return. And now what happens is we've already gone down this recursion many levels, many inception levels down this recursive stack, and now we're returning back up. So when n equals 0, we're returning 1. And this basically flows all the way back. So when factorial recursive was called with 1 as the parameter, we remember that this else statement said return 1 times whatever the factorial recursive of 0 is. Well, we know what the factorial recursive of 0 is. It's 1. So factorial recursive of 1 returns 1 times 1. Well, okay, now that we know that, what does factorial recursive of 2 return? Well, n is 2, and we know that factorial recursive of 1 was 1, so that's going to return 2. Now we work back up. What did factorial recursive of 3 return? Well, factorial recursive of 3 is going to return 3 times factorial recursive of 2. Factorial recursive of 2 was 2, so 3 times 2 is 6. Going up to factorial recursive of 4, that's going to return 4 times the result of factorial recursive of 3, which was 6. So 4 times 6, 24. And then it goes back up to 5. 5 times 24 is... So factorial of 5 is 120. So that's essentially how recursion works. It's the idea of a function calling itself over and over again until it reaches a base case. And then all those values get returned and funneled back up to return a result. Now, how does this actually correlate to our maze solving function? Well, let's go back to the maze and let's try to compare. So comparing the maze to recursion, we can see that there are similarities. Every time you're on a tile, you're essentially performing the same operation unless you're at a dead end. So right here, you're looking for all the available paths and you're exploring one of them. Now we're here. We're looking at all available paths and we're exploring one of them. Well, there's only one available path, so let's explore that path. Now we're here, we're looking at all available paths. There is none. So now we need to return. So we return. And then we're here, we've explored all available paths, let's return. It may not be super easy to visualize right now, but as we get the code going, you'll kind of see where the similarities are between this factorial function and then solving this maze. So now that we've spent time understanding how mazes work by reading the documentation, and we've covered some of the topics behind like recursion and depth first search, let's go into actually trying to write the code. And I'm going to start by just writing pseudocode. This might not be real working Python code at first, but trying to get something started. So let's go ahead and try writing some code. Let's just try to do one iteration of solving the treasure. So the first thing we want to do, let's clear out everything, get a fresh template, and let's plant a bush. Gonna plant a bush, and now let's use our little handy formula to determine how much weird substance to plant. So I've added in the little handy formula to determine how much substance to plant. Right now it's using world size, but instead let's actually stick with our smaller grid. So grid size we'll set to 5, and instead of our total world size, let's do grid size. So now with this code, this should create a treasure, and it should create a maze. So before we go any further, let's just actually make sure this is working. So I'm gonna hit play, and there we go. It did create a 5x5 maze. So that's good, let's keep going. So going back to our discussion of how we would actually solve this maze, the idea was that wherever we are, we want to look at all the available paths and explore those different paths. So essentially what we want to do is for every direction available, let's explore that path. So for direction in all directions, explore that path. And I'm going to define all directions as all possible directions that we can travel, which are north, south, east, and west. Now let's define this explore path method here. So in this explore path method, what should we do? Let's suppose that south was passed into this explore path method. If we're at the starting position and we want to go south, really nothing should happen. So what we can do here is we can say, if not move direction, let's just return. So the move function, it will either move to the desired grid and return true, or it will attempt to move and be unable to, and it'll return false. So by going into this condition, if we can't move, this is essentially saying that there is no path in this direction. So now the next thing I want to check for is if we're on top of a treasure. As we're exploring, at any time we could be above the treasure, and if we are, let's just harvest it, and that's completed. So we harvest and return. And that's our goal right there. If we're above a cell with treasure, let's just return and be done. We did it. Now let's think of the scenario where we've just traveled north. So we started right here as this farmer. In fact, let me just move north to visualize this. Move north. So suppose the last thing that we did was move north from this position here. So from here, we want to try every possible path again, just like we did before, where we're going through every possible path and exploring. Even here, we want to explore every possible path. Now in reality, we can't go left, which is west. We can't go east. We can't go either west or east because there's a wall. We can go south, but we don't want to because we just came from that direction. So we need to handle that specific case. So for explore direction in all directions, if this direction is where we just came from, skip. So we can say this. So what we can do here is we can say that if, and let's make up a fake function that doesn't exist yet called opposite direction, explore direction equals direction. So what this is saying is that if we're in this position right here, and our explore direction is going to be south, so we're passing in south to this made up function called opposite direction. This is going to return north, so which is the direction that we came from, in which case we do not want to travel in that direction. So what we'll do is we will continue. Continue is just a way of saying skip this iteration of the for loop and go to the next one. Now let's define this opposite direction function. Opposite direction. There are probably a few ways that we can do this. In some ways they're a lot more efficient, but I'm just going to pull in some sample code that just handles every single scenario. So if the direction's north, let's return south. If it's east, return west, and so on and so forth. And this will ensure that for whatever direction's passed in, we're going to get the opposite direction returned. So now this portion of the code should work. If we're trying to explore south from this position, we don't want to do that because we had just come from this position. So south passed into opposite direction comes out as north, and that equals north, so we'll continue. Now, if our explored direction is not the direction that is not the cell that we just came from, we can now pass it into our recursive functions. What we'll say is explore path, explore direction. So the idea here is that we are going to explore in the desired direction. Now this for loop is going to go through. It's going to first try, what direction will it try first? It'll try north first. It's going to go north and it will successfully move. So it's going to go into this method. It will successfully move north, so it will not go into this return function here. It won't find the treasure, so it'll skip this. And then from this cell here, so it moved north, and from here, it is going to explore all directions. And again, this will ensure that we don't go backwards, and then this will explore the path for all of the directions. And assuming we get to the point where we're trying to explore in a direction that has a wall, that portion is handled by this code right here. Because this move will return false because we can't move that direction, and we'll simply return. Okay, let's try out this code and see where it's at right now. Oh, tabs. Got to fix all the tabs and indentation. All right, now that the indentation is fixed, let's try running this and see what happens. I think it did it, but let's go through this and see what happened. Okay, I'm realizing that what's happening here is that when we see the treasure, we're not actually exiting. So when we return, let's actually return a Boolean value. So true will mean that we've completed everything, and false means that the treasure hasn't been found yet and we need to continue exploring. And what we'll also do is when we run this explore path, we'll say if, that way we're checking the return value. So if explore path returns true, which means we found a treasure, then we will also return true from here so that we can funnel this explore path all the way back up. And we'll also break if we get right here and we found the treasure. All right, now let's run it. Okay, so I implemented this slightly different than I've done in the past, and I'm trying to see what the issue is, because it can get into a scenario where it either gets stuck or it gets into an infinite loop. Okay, I just noticed I missed a very important part of this algorithm here. So once you've explored a path and you've explored every possible intersection within that path, if you don't find the treasure, you need to actually backtrack. So the thing I missed here was that we need to move opposite direction of the direction we came from. This will make it so that if we go all the way to an end of the path and we haven't found the treasure yet, we actually recurse all the way back up. So let's run this and see what happens. So now that we have an algorithm that finds the treasure, we don't want to stop once we just find a single treasure. We want this to loop continuously because the goal, probably where you're at in this game right now, is that you need to build up as much treasure as possible to unlock more things in the unlock tree. So let's update this code to actually run in a loop. So what we'll do is we'll wrap this bottom part in a while true. Let's indent this all out and let's go ahead and run this. So there it goes. Now we've got a script that's running through, exploring the paths, finding treasures, and you can see that your gold amount is going to be building up very fast. And now that we've got something working, we don't want to limit ourselves to this 5x5 grid anymore. We want to maximize the amount of gold that we're getting. So let's stop this. Instead of grid size, let's do get world size, because that will get us the maximum amount of gold for our algorithm. So let's go ahead and run this. And there we go. We're exploring the maze efficiently, and we're finding treasure. And hopefully this helps you guys to progress within the game. So let's walk through the code and let's make sure we understand what's happening here. So we're in a while true loop, which means that we're going to be looping over this code over and over again. At the start, each time we're clearing, that means we're deleting whatever maze existed before, and we're just planting, or we're just resetting the maze, and we're just resetting the farm to its default state. We're planting the bush, and we're using weird substance on a bush. That's the thing that initializes the maze. Then from wherever we're at, we're going to explore every possible option. This goes back to the idea that we talked about of how we actually go through this maze, how we would do it in reality. So we're here, we're going to try going this path. So what we do is we see if we can move. This path we can, so we do move, we skip over this return false. Now we try to get entity, now we try to see if there's a treasure below us. There's not, so we skip over this. And then from this position, we're actually going to explore all possible directions. So from here, we're going to attempt to go west. We can't go west because there's a wall. We're going to attempt to go north. We can't because there's a wall. We're going to attempt to go east. We can't because there's a wall. We've tried every possible, and we're also going to attempt to go the opposite direction, but because of this check right here, we're going to see that that's actually the direction that we came from. So we're not going to go that way either. So we've gone through all this code within this explore path and nothing happened. So now what we need to do is we need to move the opposite direction of what we came. So now we are going to move back to where we started right here. All right, so we've tried this path and we've ruled that out. Now let's go to our next direction. Let's say our next direction is this path here. We're going west. If not move direction, we're going to move direction west. That'll be successful. So we can move west. We'll skip over that part. The treasure's not there. We're skipping over this part as well. And then from here, we're going to explore all directions. Let's say we try west first. There's a wall there. We can't go there. We try north next. That succeeds. So we explore path north. And you can see how this keeps going on and on. We're using the same exact algorithm at each position we're at. And this enables us to ensure that at every cell we go to, every possible path from there and all the intersections from that path are all explored. And this will guarantee that we will eventually find the treasure. Okay, so a really good way to visualize what's going on in the algorithm is to use breakpoints and take a look at all the local variables as we go through. So let's go ahead and kick off the script. Okay, so we've got a brand new maze here and we're on the bottom left right here. Now what's happened so far, it's initialized the maze and it is going through every direction. So the first direction it's trying, let's see, is north. So it's going to try to move north here. And actually what's going to happen? Well, there's a wall right there. So what should happen is it fails to move and it should go into this return false and return. So let's go step by step and see if that's what happens. Yep, we can see it went into the return false here. And we get kicked back out to the upper for loop. So now it's going to enter the next direction. It looks like that is south this time. So what's going to happen when it tries to go south? The same exact thing. It's going to fail to go south. It's going to return false. All right, now we're in the next iteration. The direction it tried to go was east, and you can see it actually did move east successfully, so it shouldn't go into this false. Let's let it run until the next breakpoint, which is this iteration here. So it skipped past this if statement here because the treasure was not below it. And now we're iterating through all directions from this cell right here. So the very first iteration, which one are we doing? We are trying north. The first check it's doing is actually checking if north is the direction that we just came from. And it's not, so it should not go into this continue right here. Let me set a breakpoint right here. So yep, it skipped this continue, and now it's going on to explore the path, which is north. So let's go into this explore path. So now it's in the recursed explore path method. It's going to try to move north. It did successfully move north. It's again going to check for the treasure. Let's bypass that. And now from this cell, it's again going to explore all the different directions that are available in this cell. Setting these breakpoints here is a really good way for you to test out this algorithm and go step by step to see what's actually happening. So I just wanted to showcase that really quick. I'm not going to go through the entire algorithm, but this is just a great way to really get an idea for what's happening. So hopefully this explanation kind of made sense to you guys. I mean, recursion is a complicated concept in computer science. And as someone who's worked in software engineering for many years, this is something that I can work through, but if you're new to programming, this is going to be confusing. And hopefully this at least exposed you to what recursion is and how to solve problems like this, where whatever problem you're solving can be first solved by solving for the subset and then propagating that back up to the overall problem. So if you found this confusing and you couldn't really follow along, just leave a comment and I'll try to respond with clarifications. Hopefully this was at least somewhat reasonable to follow, and maybe this inspires you to learn more about recursion, to learn more about the idea of depth first search on a tree. And hopefully this unblocks you on your journey to getting all the unlocks done on your farm. Best of luck to you, and hopefully this lets you progress within the game.